Hello, welcome to this video. So in this video we'll be talking about getting the mechanics of particles from the idea of the action. Now getting it from the action is actually relatively straightforward because through considering the action as a Lorentz invariant quantity with the units of energy times time, we can get to a Lagrangian, and once we have a Lagrangian, we can use the ideas in Lagrangian mechanics to get to the relativistic momentum and energy of a particle. Now in this playlist we've seen how to get to relativistic momentum and energy through the geometry of space-time, but you can also do it from a dynamical perspective where we make use of the Lagrangian. And given this channel includes many different areas of physics, I thought it'd be nice to intertwine the idea of the Lagrangian, usually seen in more advanced versions of classical mechanics, with the ideas we have seen when we have looked at relativity. So if we're going to be looking at kind of what the action is, in order to get the Lagrangian and therefore to get some expressions for the relativistic energy and relativistic momentum, we need to take a step back and think generically, not just in the context of relativity, but generically what do we mean by the Lagrangian. Now it's complicated by the fact that when physicists say the Lagrangian, they could mean the Lagrangian, which is the L in normal kind of Roman font, or they could mean the Lagrangian density, which has the symbol curly L. Now in quantum field theory, you're always using the Lagrangian density, and drawing a curly L all the time is tedious, so you'll see normal L, but they mean the Lagrangian density, not the Lagrangian. However, the Lagrangian density and the Lagrangian are very similarly connected. So the Lagrangian density is a combination of energy densities, so densities across space, that describe the dynamics of our system. Now if you integrate Lagrangian density over space-time, you're therefore integrating energy density over space-time, so you're going to get energy integrated over time, and that kind of energy is a Lagrangian, just normal Lagrangian. So the Lagrangian is a combination of energies, the Lagrangian density is a combination of energy densities. But the cool thing with the Lagrangian density is it shows that, the idea of the Lagrangian has a relativistic footing. It makes sense to talk about the Lagrangian because we can essentially think of the Lagrangian density as a combination of energies, or alternately the concentration of the action in space-time. Now, to get to the action, which will in turn help us work out what the Lagrangian is, we need to consider the units of the action. So either by thinking of the action as the integral of the Lagrangian density over space-time, or thinking of the action as the integral of the Lagrangian over time, we get that the action has to have units of joule seconds. So we want our action for our free, and we're going to be working with free relativistic particles, so particles that aren't experiencing any forces but may well be moving, at relativistic speeds. We would like the action describing the motion of such particles to be Lorentz invariant, and that's because the fundamental symmetry that defines special relativity is of Lorentz invariance. So things like the size of four vectors or the value of Lorentz scalars not changing when we jump reference frames, so mathematically when we undertake a Lorentz transformation. So we would like action to have units of joule seconds, and we would like it to be Lorentz invariant, and the simplest way of satisfying both of these things, if we pick an energy which is a Lorentz invariant, a time that is a Lorentz invariant, and we combine them together by multiplying them to get the action. So, we know energy is not always going to be a Lorentz invariant, but one type of energy that will be is the Ross mass energy, because the Ross mass energy is the result of taking a scalar product of a 4-vector with itself, and special relativity tells us that the scalar product between any two 4 vectors is a Lorentz invariant quantity. So the Ross mass energy, mc squared, is going to be Lorentz invariant, so we might guess that the action is mc squared times time t. But the thing is, okay, we've got a relativistic, we've got like a Lorentz invariant energy, mc squared, but time isn't Lorentz invariant usually. There's a special time because of how it's defined in relation to motion that is Lorentz invariant, and that time is, you can also think of it as being Lorentz invariant because that special time, which we'll call the proper time, so the proper time is related to the space-time interval. The space-time interval is a Lorentz invariant because the space-time interval we get from taking the scalar product of 4 position with itself. So another scalar product of 4 vectors, so the space-time interval and therefore proper time are both Lorentz invariant quantities. And so our action we can think of as mass times the speed of light times the integral of our space-time interval. Now I'm using the term integral to keep things general. Now, the important thing to note here, capital S is the action. So in our case, a Lorentz invariant quantity with the units of joule seconds. ds is a infinitesimal space-time interval. So small s and capital S are fulfilling very different roles. Just something to bear in mind. So we've seen what the action for a relativistic free particle should be. We're now going to look at the Lagrangian, and from the Lagrangian get the relativistic momentum, and in the next bit of this video we're going to get the relativistic energy. So the action is this thing, and if we want to get a Lagrangian from it that will be kind of useful, we have to consider whether we want to stick with proper time and its relationship to the space-time interval, or whether we want to talk about more generic time t. Well, when something's having momentum relative to us, or kinetic energy relative to us, we have time dilation kicking in. And time dilation prevents our measurements of time, so our kind of time t, matching the proper time, so the time the moving object perceives as passing. And so since we are trying to describe the relativistic momentum and energy of something, that thing has to be moving relative to us, so the time we really want to use is our time that will be different to the proper time. But we can use the fact that the proper time tau, or thinking of an infinitesimal amount of proper time d tau, and an infinitesimal amount of r time dt are related by the relationship that d tau is dt over gamma. And since ds is c d tau, ds is therefore gamma to the minus 1 times c dt. And if you would like to have a look a bit more at Lorentz transformations and time dilations, I would recommend heading back to the beginning of this playlist where we talk about Lorentz transformations and that kind of thing in a fair amount of depth. But substituting our expression for the infinitesimal space-time interval into our equation for the action, we end up with this bottom equation, and now we can get a Lagrangian. So the Lagrangian is going to allow us to talk about our description of the object that is moving relative to us. To work out momentum and energy from the Lagrangian, we want to write this gamma to the -1 inside the integral more explicitly. So if you use if you use how gamma relates to generalized velocity, so x dot, where x dot is the time derivative of generalized position, so x dot is generalized velocity. If you use the relationship between gamma and generalized velocity, you can easily show that gamma -1 is the same as 1 minus x dot squared over c squared, all to the power of a half. That just comes from a definition of gamma, or as we should call it, the Lorentz factor. Now, recall that the action we can write as being equal to the integral of the Lagrangian over time, and so if we just look at our expression for the action, we can see that the Lagrangian should be the expression we have in our right hand box. And now we've got our Lagrangian, we can use standard techniques from classical mechanics to get the relativistic momentum and relativistic energy. So the relativistic momentum is defined by the partial derivative of the Lagrangian with respect to generalized velocity, and when working out the partial derivative, we use the chain rule, and you end up with this expression. The two minus signs do cancel out, and that's why we put a minus sign next to our action to begin with. The minus sign doesn't change the units of the action, it doesn't prevent it being Lorentz invariant, so we're free to put a minus sign there. And it just means when we go on to find the momentum, we won't end up with anything that is negative, because our kind of minus signs from the chain rule and our minus sign in front of the action cancel out to leave us with positive momentum. And then we have this expression for the momentum, which we can simplify to this. So this is telling us that from our perspective, as we're seeing something move away, its relativistic momentum is mass times its velocity times by the Lorentz factor. And this is exactly the equation we got when we were looking at things like Rass mass and things like form momentum in previous kind of videos. And, you know, it's worth saying that as the velocity approaches the speed of light, this relativistic momentum deviates significantly from the prediction of Newtonian mechanics. And this also shows that, you know, the idea of getting the dynamics from the Lagrangian, and therefore ultimately from the action, the idea extends beyond just the classical mechanics where one would usually be using the technique. It does work perfectly fine for relativity also. So to get the relativistic energy, we make use of, again, something you might have seen in advanced classical mechanics, and the Hamiltonian, which we define to be the generalized momentum times the generalized velocity minus the Lagrangian, and using our equation for the Lagrangian and generalized momentum, so here generalized momentum means the relativistic momentum, we get this expression for the Hamiltonian, so the total relativistic energy of the particle moving away from us. And then if we use the equation that if we use the definition, even really before we use the definition of the Lorentz factor gamma, it's helpful to pull out a m times gamma to give us gamma to the minus 2 on one of our terms. And that's helpful because gamma has a square root, so if you either have gamma squared or gamma to the minus 2, or in general gamma to the n, where n is some even integer, the square root goes away, which makes rearranging things a lot easier. If you use the expression for gamma squared, you can easily work out what gamma to the minus 2 is. So gamma squared would be c squared divided by c squared minus v squared, and so you can easily get from that what gamma to the minus 2 will be, and then if you substitute that in, you'll notice a term in gamma to the minus 2 will cancel out with a c squared, and we'll be left with c squared minus x dot squared within our brackets, within our, I suppose, within the second set of brackets. So that's everything that's left over from c squared times gamma to the minus 2. And then we look at the whole expression for the Hamiltonian, and we have x dot squared plus minus x dot squared, so x dot squareds cancel, and we're left with the relativistic energy is mc squared gamma, which is exactly what we would have predicted from our discussion of kind of the energy of particles in special relativity. So I think that's kind of quite cool. So an interesting fact I kind of came up on, because as I was doing this video I was trying to think, okay, what really is the Lagrangian for a free particle? Now the Lagrangian is usually fairly easy to distinguish from the Hamiltonian for a free particle, for a particle, because we're usually dealing with particles that are experiencing forces, and in such a case the Lagrangian is noticeably different from the Hamiltonian. But in a case where there are no forces acting on the particle, I was thinking, well, how should I think about the Lagrangian? What kind of picture should I be presenting? But we looked at our expression for the Hamiltonian and the Lagrangian, and ultimately the definition of gamma in terms of time dilation, so in terms of the derivative of proper time with respect to coordinate time t, we see that there is a natural connection between the Hamiltonian and the Lagrangian, in that if we take the Hamiltonian and square root it, and we say integrate that over coordinate time t, well, that's equivalent to integrating the square root of the Lagrangian over proper time tau. Now, I'm not too sure on exactly what this equation is saying, but I think it's quite cool that the Hamiltonian and Lagrangian seem to be related ultimately through some kind of Lorentz transformation-like thing. Now I'm hoping to do a little bit more look at that later on. I'm aware that sentence wasn't grammatically correct, but one thing with doing a lot of maths is one's ability to use English grammar does just drop for a little bit, because maths has a very different structure to English. If you do very heavily mathematical exams, it might be something you're fairly familiar with. I remember with one of my friends after a physics exam, neither of us could clearly communicate really using the English language, because we had just done, I think it was probably something like 2 hours of maths involving multivariable calculus and many different things. But anyway, that's everything really for this video. So the next video that I'll put on the playlist after this one will be one on the energy momentum tensor, again building on the idea of energy. Now in that video I'll be taking the speed of light to just equal 1, since the energy momentum tensor is something particle physicists love, as well as cosmologists looking at relativity, and there we often use the convention that C is just equal to 1. But for those of you who are thinking, has a video on energy momentum tensor already appeared on this channel? Well, I technically made it yesterday. I've changed one small kind of detail in the written explanation for it, so I'll be re-uploading that video along with this video. But also that allows me to put the energy momentum tensor after this video. So yeah, next video in the channel, energy momentum tensor, and then we'll look at paradoxes. I am hoping at time to do a kind of finish off our discussion of tachyons. But the idea of tachyons seems so splintered in research. I'll wait till there's a more unified picture to go with, because nobody really knows what to make of tachyons really beyond their kind of core description. But anyway, that's where we're going, with this playlist. I hope you got something out of this video. I hope you have a wonderful day ahead, and I look forward to sharing with you some more wonderful physics soon.